And I'm just going to use addition in this example, but subtraction, multiplication, division work exactly the same way. Remember, with combinations of functions, we started with a single output, and then we had two separate functions, or sorry, a single input, and we had two separate functions. And I put the same input into each of the functions individually. And so this gave me an output of f of x, and this gave me an output of g of x. And then once I got the two individual outputs, we added those together, and that gave us f plus g of x. So that's what we did yesterday. Today we are talking about compositions. When we take the composition of two functions, again, we have two different functions, but instead of evaluating them individually and then doing something with the two outputs that we get, we're evaluating them consecutively. So we're going to take a single input, x, and we are going to put that into one of the functions. So we'll put it into f, which gives us an output of f of x. And then I'm going to take that output and use it as the input of my second function. So we are going to plug that number into g, and the resulting function is the composition of f and g. It is g of whatever I plugged into g. In this case, I plugged f of x into g. So g of f of x. So this comes in handy for writing new functions. Like, for instance, suppose I had, suppose you have a square. We know that if the side of the square is s, then the area of the square is given by s squared. But then suppose we have, how do I want to do this? Oh yeah, let's do this. Let's say this square is my bedroom, and I'm trying to carpet it, right? And I'm going to buy some carpet, and the cost of the carpet is, say, $4.25 per square foot. So I can say my cost function takes an input of the area of carpet that I'm buying, right? And it gives me a cost. So the cost is $4.25 times A. Well, it would be nice if I could just measure one side of my room and plug that into a cost function and know how much I'm going to spend on carpet, right? So if I take A of S and I plug it into C, then I can get a function that has an input of S and an output of cost. So C of A of S is C of S squared, which is 425 times S squared. Right? We're just saying that S squared is the area of carpet I need to buy. And if I multiply that by the cost per square foot, that'll give me the total cost. So now, instead of measuring the length of the wall, calculating the area from that, and then calculating the cost from the area, I can measure the length of the wall and put it directly into this formula to get the cost in one calculation instead of having to do it repeatedly. Does that make sense? So that's where this comes into play, is that often we have several relationships that relate several different variables, and if we can take compositions of the function, we can go from one variable all the way to another without having to go through multiple functions just by writing a new function. So let's do a few of these. Let's let f of x be 4x plus 1, g of x be x over x minus 2, and h of x be the square root of x plus 3. So the key to doing this without getting all tripped up is just like when we first started evaluating functions, is to think of a function as a rule, not as something that has to do with x. So f of x equals 4x plus 1. What that is saying that f of whatever your input is equal to 4 times your input plus 1. So it's just giving a rule, so a set of operations that you do with whatever you're plugging in. If you get hung up on the x, it gets really confusing because there are x's all over the place, right? So we want to think of whatever is in the parentheses as our input, and then that rule as operations that we do to our input. So if I want to find and simplify let's start with f of h of x. This is just an alternate notation for f of h of x. So when you see the notation on the left, the first thing you should do is write it in the form on the right. Sometimes they'll just give it to you in the form on the right, but this notation, I really don't like it personally, but that little circle isn't like the letter O. It's like it when you see it in your textbook, it's kind of like a multiplication symbol, but it's open, right? So it's just a little tiny circle. I feel like there's one person in here, maybe it's in my other class, that does their multiplication symbols like little circles and not like dots. So that'll be a problem, but maybe it's not in this class. But so when you see that, you can sort of think of it as an O. So it's like f of h, right? And that just means f evaluated for an input of h of x. And like you won't use that that notation doesn't do anything for you mathematically. It just tells you to write it like that, and then you're done with it. So you want to work from the inside out. So remember, you're always starting with your input. So we start with x. So starting with the x, the first thing we want to do is apply h. So that is saying take f of, let's write it with, whoa, that was big. So the first thing I want to do is replace h of x with h of x. So h of x is the square root of x plus 3. So that's what we're going to use as our input. And f tells me to take my input, multiply it by 4, and then add 1. So f of the square root of x plus 3 is going to be 4 times the square root of x plus 3 plus 1. So we can kind of think of this as just like a substitution. So you want to substitute the square root of x plus 3 for h of x, and then substitute that in for your input in your second function. If you take it step by step, these go pretty smoothly. Where they get really confusing is when you kind of try to do them all at once, because like I said, there's so many x's floating around, it's easy to get them confused. So let's try another one. Let's do...
So that's your answer?
Uh-huh. That can't be simplified anymore, right? Because the square root, or my radicand doesn't have any perfect square factor, so there's nothing I can do to simplify.
So h of x in parentheses, that's an input within itself.
Well, x is the input of h, right? So the output of h of x is that square root of x plus 3, which we then use as an input for f. So like in that diagram that we did before, we're taking x, we're putting it into h, and what we get out is the square root of x plus 3, which we're then putting into f, which gives us 4 times the square root of x plus 3 plus 1. Yes?
Where did the x from 4x go? 'Cause
Well, so that's the thing, is we don't want to think of it as an x, we want to think of it as an input. F of the input is equal to 4 times the input plus 1. Don't get hung up on the x. Our input is the square root of x plus 3. So we do 4 times that input plus 1. So when we write functions, like the formula for functions, the x's, all they are is like dummy inputs. They're just placeholders, really, like something to represent some general input so that we don't write the word input. But what this function really says is like f of our input is equal to 4 times our input plus 1. It really has nothing to do with x whatsoever. That's just a placeholder. I used to, when I taught high school, we'd like come up with our own inputs and use like little flowers and like houses. It was very fun. But the point being just that you can put anything into it. You're just performing that rule on whatever your input is. So let's do g of f of x. So again, the first thing you want to do is just write this as the composition of two functions. So this is g of f of x. So we'll start by just replacing f of x with 4x plus 1. So we have g of 4x plus 1. And then the function g says take your input and divide it by your input minus 2. So we've got our input, which is 4x plus 1, divided by our input minus 2. And then that one we can simplify a bit, right? We can combine like terms in the denominator. So 4x plus 1 over 4x minus 1. Questions? Does this make sense? Again, like the best advice I can give you about these is to think of them in pieces, not in like as one whole thing. So think of like, what is f of x? And just like literally replace it. And then think about applying g. If you try to do everything at once, it gets pretty confusing. So let's do how about f of x? So again, this can seem kind of weird because we're using the same function twice, but the function just says take your input, multiply it by 4, and add 1, which I can do with anything I want, right? And I can do that repeatedly. I can take a number, multiply it by 4, and add 1, and then take that number, multiply it by 4, and add 1, then take that number, multiply it by 4, and add 1, right? all I want. So I'm just applying a function twice. So we are finding f of x. So first thing we want to do is replace f of x with 4x plus 1. And then my input is 4x plus 1, which I want to multiply by 4 and add 1 to. So 4 times my input plus 1, which I can then simplify. So 16x plus 5. Yeah? You guys try, how about h of f of x? Go ahead and find that and then simplify it as much as you can. Add 3 and then take the square root, right? So we will take our input, add 3, and then take the square root. Did you guys simplify this? This one was fun to simplify. So the square root of 4x plus 4. If I want to simplify that, what's the first thing I should do? If I go like this, does it help? Yeah, I'm going to factor the inside, right? So remember that when we simplify a radical, the first thing we do is factor the radicand. If there's addition or subtraction in there, we have to factor the whole thing as a polynomial. We can't do individual terms. So we want to write the whole radicand as multiplication. So this is the square root of 4 times x plus 1. Well, the square root of 4 is 2, and then the square root of x plus 1 is just the square root of x plus 1. One thing you can try to remember is just like when we work with fractions, the goal here is to write the whole thing as multiplication, right? So if we look at 4x plus 1, we see that there's multiplication, 4 times x, and then there's also addition, the plus 4. Whereas down when we write 4 times x plus 1, that's all multiplication because all other operations are occurring inside parentheses. And that's our goal, is for the whole thing to only be multiplication. The other operations only happen within parentheses. So just like when we simplify fractions, the same idea here. If you simplify a radical, you have to get it to be all multiplication outside the parentheses. So you can do things to individual factors. Yes?
Let's say like it was 4x squared plus 4x.
Yep.
Would you add this here to that, factor that out?
Well, if it was 4x squared plus 4x, we would factor 4x out first.
Okay. But you wouldn't like add a 0 at the end, factor that down, and then 2.
Well, so if we had this, the first thing to do to factor that is to factor out the GCF, right? If we had, so this would be 4x times x plus 1, which would just be like that. If, I think that maybe what you're asking, so let me write one that applies to that. Like, if it was 4x squared, like plus like 1, then yes, you'd put the 0, or well, 1 plus 1 wouldn't work, but like minus 1, you'd put that 0 in, and it would end up factoring as 2x plus 1 times 2x minus 1, which we can't simplify because neither of those is a perfect square, so I can't take the square root of either of those. So yeah, that's exactly what you would do, is factor the entire polynomial. When I factored out my 4 here, I didn't end up with an exponent, so that's why I didn't keep going with factoring. Good. So we can also evaluate these guys for specific inputs. So like if I had, say, g of h of 5, no, 6. So that's just saying g of h of 6. And the process is going to be exactly the same. So the first thing I want to do is input 6 into h. So that gives me g of the square root of x, whoa, not x, 6 plus 3. And before you keep going, if it's just numbers like this simplify in those parentheses as much as you can before you go and plug that into g. So that's the square root of 9, which is just 3. So I want g of 3. And then we will evaluate g for an input of 3. So 3 divided by 3 minus 2, which is 3 over 1, which is 3. Lots of 3's in that one. Okay, let's look at some graph. What's wrong, Nikki?
I'm just confused.
By what?
So when you got, like, at the top, like, I guess I'm confused on when you go to the second step, like when you got g, and then times the square root of x.
So it's not multiplication, it's g of the square root of 6 plus 3. So this is saying use h of 6 as the input of g. And this is saying that h of 6 is the square root of 6 plus 3.
Oh, okay.
Like, h of 6 is the same as the square root of 6 plus 3. And so I just replaced h of 6 with that expression.
Oh, okay.
So if there's no variables, you don't like plug in for g as well, you solve for the input and then plug in for the input of g.
Yes, you simplify your input as much as possible, and then, so it's the same process, it's just that over here, like, we can't simplify 4x plus 1, so we didn't bother trying to simplify 4x plus 1. But here, like, it would be kind of a pain to do the square root of 6 plus 3 over the square root of 6 plus 3 minus 2. We could do that, but it would be a lot messier than just simplifying that all the way first. Other questions? Good. Okay, let's look at a graph. I printed these out again for you. Okay, so the process is going to be exactly the same when we're working with a graph. We just have to be really careful, again, about taking it step by step. So if I want to evaluate g or f of g of 1, then the first thing I'm going to do is replace g of 1 with whatever g of 1 is. So I'm going to write f of, and then I'm going to figure out what g of 1 is. So for g of 1, my x value is 1. And the point on g with an x value of 1 is right here. And that has a y value of 0. So I replace g of 1 with 0. And now I want f of 0. So my x value is 0. And the point on f with an x value of 0 is right here. The corresponding y value is 2. And so this is equal to 2. Take it one step at a time, because what x is not set in stone, right? Your input is 1 to begin with, which gives you an output, which you will then use as the input, right? So we can't be like, oh, but I thought x was 1, and now you're saying it's 0. It changes because x is always your input, whatever it happens to be. So again, if you just take it one step at a time instead of trying to look at it all at once. So the first thing on this second one is we want to find what f of negative 4 is. So we're going to do g of whatever we get for that. So if my x value is negative 4, here is the point on f with an x value of negative 4. The y value of that point is negative 2. And then now we want to find g of negative 2. So my x value is negative 2. The point on g with an x value of negative 2 is right there. That has a y value of 1. You guys want to try the other two? Okay. Do C and D. So find f of negative 1 first and replace it. And then evaluate that. Is 1, and that gives us 3. So then g of 4, we start with what is g of 4. So we find an x value of 4, and that gives me 1. And then I want to find g of 1. So x value of 1 on the graph of g gives me 0. Good. Now we're going to do the same thing with a table. Everybody good with those? Okay. So with the table, the process is exactly the same. We're just using the table to find the outputs instead of the graph. So f of g of 1, first thing I'm going to do is replace g of 1 with that output. So my input is 1. If I plug that into g, I get 0. So I'm finding f of 0. My input is 0. Plugging that into 1 gives me negative. Sorry, plugging that into f gives me negative 2. So here we are starting with f of 1. So my input's 1. Plug that into f. We get 0. And now using an input of 0, plugging that into g gives me 2. Let's do one more together. My input is negative 2. Plugging that into g gives me negative 2. And now my input is negative 2. Plugging that into f gives me 0. Okay, you guys try those last two. And then we'll be done. We're going to get done early today.